Okay, so after the basic discussion of what is an algorithm, what is the asymptotic analysis of algorithm, and step counting based um, cost calculation shown in the insertion sort, we come to the merge sort. Okay, merge sort um, is an example of a algorithmic paradigm, so which is called divide and conquer. So similar multiple divide and conquer type paradigms are there. Some of them are called greedy paradigm, some of them are called dynamic programming paradigm, some are other strategies. So the basic thing what I'm trying to say that we will discuss multiple such paradigms, and then we'll see the properties of those paradigms, and based on those properties, when you find a new problem, we'll try to identify, oh, can I solve it using divide and conquer, can I solve it using greedy, and in that way. Okay, so what is divide and conquer? As the name suggests, you divide a problem into multiple smaller problems which are of the same nature but of smaller size. Okay, it's like how we define it. You see, we say that divide, these are three steps. Okay, the step one is divide the problem into a number of sub-problems that are smaller instances of the same problem. So the size, that means the input size, is smaller. Okay, but the problem actually remains same. Okay, then what we do? We do conquer. What is conquer? Conquer is what they are doing, recursively solving the same sub-problems. They conquer the sub-problems by solving them recursively. Okay, if the sub-problem sizes are small enough, however, just solve the sub-problem in a straightforward manner. What does it mean here by straightforward manner? It means, suppose there is only one element in an array. We can assume that this is a sorted array. Single element array is a sorted array. So these are called base cases of recursion. Okay, so base case, we can assume that it is solved in a constant time, and the constant time is written as a theta1. Okay, this is important. So we have already learned the theta notation. So constant times will be written as theta1. That okay. So now the third step is combine. Combine. The first step is divide. The second step is conquer, and the third step is combine. Okay, what does it do? Combine the solutions to the subproblems into the solution to the original problem. Okay, so let me explain this with an example. The example is of merge sort. Okay, so what we do, we say that initially the first line of the pseudocode, I already talked about pseudocode. If n equal to 1, done. What does it mean? It means a single element array, and if this is a single element array, we consider this is already sorted. This case is the base case. Okay, so this just solve the subproblems in a straightforward manner if the subproblem size are small enough. So this is the base case of recursion. Otherwise, recursively sort a1 to n by 2 and a n by 2 plus 1 to n. Okay, so you see the array, suppose there are like 10 elements, so we divide in 5 and 5. Okay, what about when there is 5 element? We just do this. Okay, so and then the other part can be just the, okay, so one side can be like 3 elements, the other side is like 2 elements, in that way. Okay, so we can recursively keep doing this. So in merge sort, every time we divide the input size by 2, okay, n by 2, and then the input size. So initially, suppose the size of the input array was n. So next time the input array size will be n by 2. So we can just ignore the floor and ceiling just for the sake of simplicity. Okay, so next time it will be n by 4. Next time it will be n by 8 until it becomes 1. At the stage it becomes 1, so it's a single element array. If n equal to 1, we are considering, okay, that's done. So this the complexity of this step is theta of 1. Okay, theta of 1. Now this thing, how I'll write this thing when I do the time complexity analysis, I consider the time complexity of merge sort is suppose T of n, because the n is the input array, input size. Okay, now when I input this sub problem of half size of n, like I shown you, n by 2, then there are two sub problems. Okay, the first one is T of n by 2 time it will take if the whole problem with n elements take Tn time, then the sub problem with n by 2 elements will take T of n by 2 time, and then there is another sub problem with the the remaining elements. So as I told you that this n by 2 will be floor and ceiling. So for the sake of simplicity, we just do not consider this here. So then there are two sub problems actually when at this recursive stage we have actually two sub problems of size n by 2. So we call it 2t n by 2. Okay, because the divide and conquer type problem, so all divide and conquer type problem will have this recursive formulation part. Okay, and then this kind of recursive formulation to add up the cost of different stages will generate you a recurrence relation. Okay, the recursive formulation generate the recurrence relation. Now the third step is merge the two sorted lists. This is actually coming from this combine. So the combine the solutions to the sub problems into the solution to the original problem. That means multiple sub lists. So initially what we do, we divide a problem in smaller parts and smaller parts and smaller parts until the sub problem size is 1. Okay, so suppose all of them are 1. Then what we do, we merge these two, whichever is smaller we put in the beginning, and then the whichever is larger we put at the end. So in that way we keep merging them until the whole array is merged. Okay, so we divide them, break them down into n equal to 1 element, the base cases, then we keep combining them in the sorted order, so that when finally all the elements are merged, this the entire tree is sorted. Okay, so this procedure of merging, which is like the combined stage of divide and conquer paradigm. So this is let's explain this with this example. So one thing I want to tell you, that the merge procedure is the most important procedure, the heart and soul of the merge sort. Okay, because other things are just a recursive coding. Okay, the merging procedure is the most important procedure. Okay, so here you see there are let me wipe this thing. So suppose there are two arrays. Okay, two sub arrays which we need to merge. Just assume that at this stage of merging, this is at some point, suppose this element and this element is like that. Okay, so we are trying to merge two sub arrays. This is like sub array A1 and this is like sub array A2. When we try to merge them, the merged list should be the sorted list. How we do that? It's a very simple procedure. We check what are the head of the queue. Okay, so for this and this, and then whichever is the smallest one, we take it out. Okay, and write at a place. Okay, so among these two, 1 is the smallest, so we write 1. We strike it out. Now the head of the list is 9 and head of this list is 2. Okay, among them we compare. Okay, see, between every pair of nodes we compare once. So among these two, 2 and 9, whichever is the smallest, 2 is smallest. Okay, see, we get 2 elements in the order from the after 2 comparisons. You see, it's easy. So now 2 is out. Now 7 is the head of this list, 9 is the head of this list. Okay, so this 1 and 2 are gone. Okay, so now among 7 and 9, whichever is the minimum, we will pick up. So 7, so this is the third comparison. So 7 comes out. So after the third comparison, third element comes out. Okay, so 7 goes out. Now the head of this queue is 13. So among 9 and 13 we compare and we take out 9. This is the fourth comparison and the fourth element comes out. Okay, so now 9 is gone. So we compare 13 and 11. 11 is the minimum. Okay, this is the fifth comparison. This is gone. Now 13 and 12 we compare. So 12 is minimum. This is the sixth comparison and the sixth element comes out. Okay, so now 12 is gone. So this A2 is empty. Now 13 is the next minimum and then 20. Okay, so see, last two elements. So every time we compare, one element comes out. So for an n element array, we make n comparisons. So the number of comparisons is actually the procedure, the computational step. So when we do merging, we actually total number of merged element is the number of comparisons we make. Like there are four here, four here. So there are total 8 elements, 8 comparisons. So actually theta of n, the cost of this step is theta of n. If there are n elements, we make n comparisons for the merging. See, then here the time cost of merge sort is actually summation of the steps. Let me delete this part now. Divide and conquer's definition we already talked. So, and we have shown that merge sort is a perfect divide and conquer algorithm where at every stage the subarray is divided in 2 parts, okay? And the merging is the procedure where we combine the partially sorted, the subarrays individually sorted, and they are merged to produce the total merged array. So now you see, so if we say the merge sorts time complexity is Tn, so we will say Tn is actually, so let's start from this one, theta of 1 plus, here you see 2Tn by 2, 2Tn by 2 plus theta of n, 3 stages, okay? Theta of n. This is for stage 1 when the base case is encountered. This is for the recursive part, okay, recursive part, and this is the merge part, okay. So now the concept in the definition of theta, we can say this theta n, if you remember asymptotic analysis, the higher order term persists and the lower order terms are dropped. So this theta 1 is the lower order term, it is actually can be combined with theta n, and or you can just say it's dropped. So we will write like this, 2t n by 2 plus theta of n, because this is the higher order term that persists. But this is not a computationally cost, we do not have it yet, okay? So we just write this recursive. This is like t of n have 2 subproblems. This means number of subproblems, okay? This thing, 2 number of subproblems, and this means the input size, okay? Input size. So this means every time n is being divided by 2, and there will be 2 such subproblems. This is the way we read, 2 subproblems, each of size n by 2, okay? And for that, theta of n is the merging cost. Now there is a very efficient way of solving this kind of recurrences. These are called recurrence relation. So for divide and conquer type problem, we have recurrence relation, okay? Recurrence relation. So now there are multiple ways of solving recurrence relations, and I will show you 2 ways of solving recurrence relation, which will give you an idea of how how this kind of problems can be tackled. Okay, let me delete this thing, and so I show you now how this problem can be solved. Okay, this is the easy thing as long as you focus and try to understand. So Tn equal to 2Tn by 2 plus theta of n. Okay, so let me write it here. Tn equal to 2Tn by 2 plus theta of n. Now when we do the real cost analysis, we have to make sure that this theta have the the embedded constant. If you remember, we said in the definition of the big theta, big omega, big O, that there is a constant, and that constant we are leading constant we actually do not consider when we do asymptotic analysis. But from here, from the asymptotic analysis, we are going to the real cost analysis. So we replace theta of n with c of n, and then we replace this entire equation with a tree structure. What is a tree structure? A tree structure will say, you see, Cn will be the root. This is one part of the cost, and then there are 2 subproblems of size n by 2. So we say t of n by 2 and t of n by 2. This is a weird way, but this is actually a weird way of representing uh, uh, this equation. Okay, this is like a summation. It says T of n by 2 plus T of n by 2 plus Cn. So this is a summation. T of n by 2 plus T of n by 2 is 2Tn by 2 plus Cn is this part, okay, the margin part. So this is the way of representing. This is called a recursion tree, and this grows stage by stage. Now what we do, we have to, in this equation, if we put n by 2, what happens? So this becomes 2t, t of n by 2 equal to 2t n by 2 plus theta of n by 2. Okay, just for this part, So because Tn by 2 is now the input size, so we replace n with n by 2 and we'll get, just for this part, this equation. Okay, so now we will replace it like that. So how will I show you one more step? Cn, then it is written, this part will be C of n by 2, this part will be C of n by 2, and there will be two more subproblems of size, you see, T of n by 4, and this is also T of n by 4, and here also two more subproblems of size. The original input size is divided by 4, but here the n by 2 size is actually divided by 2. So now n by 4 will be input here. Instead of n, you replace it with n by 4 and then calculate the same thing, and if you continue doing that, you will find Cn has two subproblems initially, Tn by 2, which is now replaced with Cn by 2, Cn by 2, which will be divided in two parts, Cn by 4 and Cn by 4. Okay, so this is again divided in Cn by 4 and Cn by 4. Okay, now if we go on doing that, it will be C times n by 8, and this is C times n by 8, in that way for each of them. Okay, so it's a very equivalent, very balanced distribution, because every time is being divided by 2 until we go down and find there is a single element in the array, which is a one element array. Now every time it's being divided by 2, so we have to calculate at what height this, let me wipe this part, what height this, up to what height this tree will grow. So what do you think the height of the tree will be? Okay, so we need to calculate the height of the tree, and this is a perfectly balanced binary tree, and we also need to know how many leaf nodes at this level, because leaf node is the calculation. Okay, so if there is one element, if you remember, we have the cost of theta 1. Okay, so we replace this one as theta 1 cost. Okay, this is the real cost we are calculating now. So the theta 1, and there will be how many such, every time, if an n element array, you keep dividing by every time, finally every there will be n number of one element arrays. So n number of one element array, theta 1 will be n times, okay, n number of leaf nodes, n leaf nodes, we can say n leaf nodes. Now one thing is very important here. If cost of one leaf node, cost of calculation of one leaf node is theta of 1, what is the cost of calculating n leaf nodes? Is n times of theta 1, and if n is sufficiently large, so this is n times theta 1 becomes theta of n. Okay, so so for one element is theta of 1, so two elements is theta of 1, for 100 elements is theta of 1, for 1 million elements is still theta of 1. But if n tends to infinity, this does not become theta of 1 anymore, not anymore constant. The factor of n will come in here and it will become theta of n. This is a very, very important step. Now let's calculate the cost at each level. Okay, so the cost at the root level is Cn. You can see Cn, okay, at this level. Now just adding them up. Okay, this level there are two nodes, Cn by 2, Cn by 2. If you add them up, it will become Cn. 4 nodes of Cn divided by 4, so it's Cn again. Okay, so at this level there are 8 nodes of Cn, by 8 cos. So this is Cn. So how many times this Cn will be? So assume that the height h you become this becomes 1. Okay, every time you divide by at the height. So suppose this is at the ith level, n by 2 to the power I equal to 1. Assume that the ith level every time at the second level is 2 to the power 1. Here 2 to the power 0 at the 0th level. First level 2 to the power 1. Okay, 2 to the power 0, 2 to the power 1, 2 to the power 2. N by. So in that way it's going divided, n by 2 to the power 0, n by 2 to the power 3. In that way at this level, if theta 1, then assume n by 2 to the power I equal to 1. So if you take n equal to 2 to the power I, okay, so if you take log in both sides, log of n equal to I, okay, I log 2 to the base 2. So it's logarithm with the base 2, okay. So this I equal to log n. So the height of the tree, this I is the height of the tree. So this is height of the tree, okay. Height of the tree is log n. Log n is the height of a binary tree. Now this is Cn, how many times is being added? Every time except the leaf level, because we got the cost of leaf level already, okay. N number of leaf node, each theta of 1 time is theta of n. So now the cost of so now if you the height of the tree is log n. So without the last level, if you kind of multiply how many times Cn appears, log n times. So this is actually Cn multiplied by log n is the height. Every level Cn, second level Cn, third level Cn. So it's like I level Cn times log n, or log n is the height. So the total cost is for this part is Cn log n, and for this part is theta of n. So if we can sum them up, so this will become Cn log n plus theta of n, okay, which is equal to Cn log n plus theta of n equal to theta of n log n, okay. So it's theta of n log n, because Cn log n can be represented as theta of n log n, and that is larger growth rate than theta of n. So that will kind of whichever be the largest term, that will persist. So the total cost of merge sort is Cn log n plus theta n, which is theta of n log n. So that's why the merge sort's time complexity is Cn log n. So finally we get the value of Tn, which is theta of n log n. I hope you understand the details, and you can now repeat watching the video to get the basic idea. And if you have any question, feel free to ask.